So in the previous video, what we did is we found area under the curve based on some cutoff values. What we're going to do in this video is flip the order. This is going to be the idea that we're given area under the curve and we want to find the cutoff for those areas. So in this video, find the cutoff given area under the curve. So we'll see some terminology come up in here, and we're going to use Geogebra in this section as well, and it's going to be very similar to how we used it before. It's basically going to change is where we edit the information. So some terminology that we'll see come up here is the word percentile. Percentile always means area to the left. It always goes in the direction of left. So in this picture on the right-hand side here, this is showing the 70th percentile, and it's this cutoff such that 70% of the data is to the left-hand side. So visually, something to think about with our bell-shaped curve, cutting in the middle here makes 50-50, 50% to the left, 50% to the right. So where it's landing here is over to the right-hand side. It's creating a larger area because 70% is larger than 50%. So that's something we can use to kind of visualize how the values land. And if we have 70% to the left, that forces 30% to the right, because again, all the area under the curve should add up to 100%. So if they talk about some level of percentile, you're visualizing this of some area to the left-hand side. So let's look at finding these in Geogebra. Now steps are going to be very similar to what we just saw in that last video. First step will still be to edit your mean and standard deviation. So make sure those are matching up the scenario we're working with. Second step is also the same. However, the wording, it's going to come through a little different here. They'll be talking about some like lower percentage or percentile to tell you about area to the left. Maybe they'll talk about a middle percentage to be between two values, and then to the right would be some upper percentage. So those will be the higher values when you're looking at greater than, and then the other symbol when you're looking at lower values to represent less than. Now what changes is where we edit in our notation. Like before, we edited over here in our probability notation because we were plugging in the cutoff values and finding area. But what's happening here is we know area. So where you're going to edit is on the other side of the equation. So this will be your next step, is to edit the area, and your answer will show up on this side of the equation. In that probability notation will be your answer, which will be a cutoff value. So let's practice this and see how it works. But we're basically reversing, or it's even called the inverse in calculators, where what we did in the previous video was just a normal cumulative density function. What we're doing in this video is the inverse of that. So, all right, we're going to go back to our rainfall example. So we have Portland rainfall still, normally distributed with a mean of 40 and standard deviation of 8. And what we're going to do is find the cutoff value. So in the wording here, they're telling us about this lowest 10% of rainfall. Now your low values are on the left-hand side here. So we're going to be over here, and drawing a sketch for these is a little more difficult. In fact, when I draw sketches for these, I often leave out the number line. Maybe I'll still put 40 to get an idea of what's exactly midway. It's right at that 50-50 spot. But other than that, making a number line can be kind of tough here. So 10%, and I'm just going to estimate that's a small area. So I'm just going to make a small area on the left-hand side. So having the lowest values makes this left-sided. So I'm going to be over here somewhere, and now it reverses in that I don't know what number this is on the number line. What I do know is the area under the curve. I have 10% of data in that area right there, but I want to know what's that cutoff for the lowest 10%. So in terms of a notation, it can be kind of strange to write out at first, because what I'm looking for is what's the probability that x is less than or equal to, but I don't know what number goes there. But I know that probability should be equal to 10%. So we need to find the value that would fill in the blank there. So let's go to Geogebra. So we'll have our mean of 40, standard deviation of 8. This is in the same window that I was using in that previous video, so you don't need to go anywhere special. It's the same thing of go to Geogebra, more apps, and probability, edit your mean and standard deviation. Because this is the lowest 10%, this will be left-sided. So you can see right now it's doing this 84.13% of data is shaded, but I want it to be shading 10% of data. So this is where I'm going to edit on the other side of the equation, so the kind of probability side of it, and I'm making that probability 10%. Make sure you type it in as a decimal here, even though they're saying 10%. If I type in just 10 right now, it'll give me an error. You want 0.1. And if we hit enter, then that's our cutoff value right there. It's landing at 29.7476. So what we'll do is that's our solution, is that 29.7476. And this, what's coming out, our answer isn't a probability anymore. It's a value for x, which in this case is representing rainfall in Portland. So my sentence, we're looking for the lowest 10% of rainfall. I could say the cutoff for the lowest 10% of rainfall in Portland is, and then I just copy my number down, 29.7476. If you wanted to round a bit here, that's fine too in your sentence. And then in terms of units, you can look at the units for the mean and standard deviation and it'll be the same. So like our mean was 40 inches of rainfall. This cutoff is in terms of inches of rainfall. So this value also represents the 10th percentile. You can see this wording I added there. So that's what this image represents, is this lower 10%. So I could also say like the cutoff for the 10th percentile of rainfall in Portland is 29.7476 inches, or you could say like about 30 inches, or however you want to round it. Let's look at another example. So the highest 5%. So now this is going to be right-sided because we're looking at the highest values. So I'm going to be over on this right-hand side here, and 5%, it's a teeny tiny area. So I'm going to make a small area here, maybe there-ish. And again, I don't know what the cutoff is in terms of rainfall, but I know this area under the curve is 5%, or 0.05. And if you feel comfortable working in terms of area to the left, or even just to show you how these complements are working, like in part A where I have 0.1 to the left, I also have 0.9 to the right. Here, if I have 5% to the right, I have 95% to the left. So that's where you can see this notation of it saying it's the 95th percentile, and it's because 95% of the data is to the left-hand side. So even though the wording is talking about highest 5%, percentile always goes to the left, so they would use the 95 instead. So with this one, I'm looking for probability of x being larger than or equal to some number that I don't know. But the probability of it being larger than or equal to that number should be 5%. So in Geogebra, I'm going to switch to right-sided. So I'm taking area to the right, and I want that area to equal 0.05. So I hit enter, and I could see it matching the picture that I drew, and the cutoff is 53.1588. So that's our cutoff in terms of rainfall. And I'll do this one, I'm going to word this in terms of percentile just so that you can see how you would word that. I could say like the cutoff for the 95th percentile of rainfall in Portland is, and I'll go ahead and round this, let's say about 53 inches. So that's another way to word these answers. If you're answering in terms of a percentile, I could have said the highest 5% of rainfall is about the, like up above. So, all right, our last example here is a special case where we're looking for a middle 50% of rainfall. So this isn't lower or upper, it's between two values. So I'm going to be using, well, we'll kind of talk about this more, but this is leading to the between idea. So in terms of a picture, what we're doing, and this should be symmetric, I'll draw this as best I can to make it look symmetric. So right in the middle, we have 50% of our data, right in the middle there. And what I want to know is what are the cutoffs. So we're actually going to have two cutoff values for this middle 50% of rainfall. In fact, instead of just question marks there, I'm going to call this X1 and X2. So we want to find these two X values such that we have 50% of data in the middle there. So if we go to Geogebra and I change to that interval between, what you'll notice is we can't edit. You can probably even hear me clicking right now. You can't edit the area here. And the idea is to have like middle 50%, and I could try to drag these as best I can, but what'll most likely happen is I won't have it perfectly even. Like look here, I'm at about 50%, but this isn't symmetric. So I could try to adjust, and it won't end up being exactly symmetric, or it at least will be very, very hard to do. So the idea is that you can have this middle 50% occur basically anywhere with a lower bound and upper bound. And how our 50% is occurring is in a very specific way with that middle 50%, but we can't tell this to like make it centered, make it symmetric. So we need to get a little creative with how we're going to find this answer. And what we're going to use is the other areas, using the tails. Meaning for X1 right here, while it's cutting off this 50% in the middle, simultaneously, it has this area occurring to the left-hand side here. So what we could do is figure out what's happening in these tails, because X1 is going to be associated with this area to the left, and X2 is going to be associated with this area to the right. So we can use that tool that we did with the empirical rule, meaning if we have 50% in the middle, we want to think about what do we have left over, because that's what the two tails would have. So if we have 50% in the middle, we have 50% left over. So that yellow shaded area has a total area of 50% right now, so that everything adds up to 100%. And what I want to do is cut that in half. So this would be a 25%, and this would be 25%. And the key is that because they told us it's a middle 50%, we have that symmetry occurring. So if I want to find X1, what I want to think about is X1's the cutoff for this lower 25%. So I'm going to do is when I go to Geogebra to find X1, it has this probability of less than or equal to some number that we don't know yet, but that probability of being less than or equal to some number is 25%. Then to find x2, I'm going to do a similar piece, but now it would be more than or equal to. We'd be looking for that right-sided probability. So being more than or equal to some number is equal to 0.25. So if we go to GeoGebra, I'll do x1 first. So taking area to the left, and I want that area to the left to be 0.25. So we're going to have this lower bound of 34.6041. And then to find x2, same idea of going right-sided, and it's going to have a right-sided area of that 25%, which is a 45.3959. So that's going to give me my lower bound and upper bound. So this one doesn't have a percentile associated with it because it's bound between two values. So you'll notice with A and B I talked about percentile. This one is a special case. So I'd say the middle 50% of rainfall in Portland is between let's say about 35 and 45 inches, just around those to hold numbers. All right, so that's how we find cutoff values given area. And the key thing that changes is where we're editing within GeoGebra. In that last video, we edited on the left-hand side here because we were given cutoff values and wanted to find area under the curve. In this video we just went through, we edited area under the curve so that we could find the cutoff values.